Okay, I think it's a good time to start the lecture. And welcome to the Differential Privacy course. And this is the 12th lecture. And today we're hoping to wrap up our chapter on differentially private machine learning. We'll introduce and actually continue to talk about this algorithm on noisy gradient descent and noisy stochastic gradient descent mechanism. And then we'll talk about how various model of deep learning with differential privacy actually works. Some administrative notes. So the project proposal feedback, I've already submitted the feedback on Gradescope to all of you, and please take a look at them and then revise your proposal and address the issues, like if I mention any issues in the midterm report, right? So that you'll be all set to have a successful project by the end of the quarter. For the second homework, I'm finalizing the programming part of the second homework with the coding template on the Jupyter notebook. It's almost ready. I'm still testing some bits and pieces of it. Once it is ready, I'll just announce it on Piazza, and you can hop on it right away. And I think this particular lecture will be useful for you to understand some of the theoretical aspect of learning with differential privacy, and in particular, how do you set learning rate in this noisy gradient descent algorithm, like from a theoretical perspective. And you see that these choices actually would work quite nicely in practice. And if you deviate from the theoretical choices in one way or another, sometimes they don't result in like very effective algorithms. Okay, so as usual, we'll start with a recap of the last lecture, and we'll also mention some of the things that we'll be using from maybe a while ago. So in the last lecture, we compared the utility of the objective perturbation algorithm and output perturbation algorithm on the same privacy requirement. We analyze them using the tools that we learned from convex optimization. And then we talked about their limitations and moved on to a new family of iterative algorithm called gradient descent and stochastic gradient descent. And we analyzed the convergence of like one version of the convergence analysis of the stochastic gradient descent. And then at the end of the last lecture, we proposed that the noisy gradient descent mechanism where we synthetically add noise to the gradients themselves iteratively and compose over the many iterations is one instance of the stochastic gradient descent. Therefore, the convergence analysis would apply. And the privacy analysis is also somewhat simple because it's a composition of Gaussian mechanisms. So let's go over some of these items. We for the output perturbation and objective perturbation, like these are some of the early works in differentially private empirical risk minimization in the convex setting, and when we make an assumption about the loss function being just Lipschitz, then objective perturbation is no longer applicable because we're not able to make use of that Jacobian argument for the change of variable. Like this could be fixed in some cases using techniques from Kiefer et al. To handle, say, non-smooth regularization terms. But when the loss functions are not differentiable, then I don't think it's easy to show that objective perturbation satisfy any form of privacy guarantees. Like for smooth losses and smooth losses for generalized linear models and objective perturbation, like it's working really well. They are giving us results that goes to 0 at a 1/n rate, which is faster than the non-private learning rate, the non-private rate of access risk as number of data points gets larger. In contrast, objective perturbation, while it works more generally and it covers the Lipschitz loss functions as well, like it suffers from like a worse dependence on the number of data points, right? So the dependence on the number of data points are worse, and that makes it like inferior algorithm comparing to objective perturbation in many cases. So we mentioned that these two algorithms, so they are interesting and they are somewhat clean, but the results that they are getting are not entirely satisfactory, except for a very restricted setting on the generalized linear models. So they require the loss to be twice differentiable and do not handle the constrained convex empirical risk minimization, like when there's a pre-specified feasible region of the parameter vector that you have to use. They also do not handle the case when the empirical risk minimization problem have non-convex losses with respect to the parameters. This exclude all the useful family of deep neural networks from being privately trained using these two approaches. Okay, so that another thing that I'd like to give you to revisit. So this was from a while ago when we were talking about DP physics. So recall that epsilon delta DP is not like a satisfactory description. It's too concise a description to measure the performance of a private mechanism. And we said that when we there's another family of mechanisms where its privacy loss random variables are sub-Gaussian, and then by leveraging that sub-Gaussian property, we can show that the family of mechanisms satisfies these properties. They satisfy something called a zero-centered concentrated differential privacy, or ZCDP. Right? Slightly more generally, when we use the entire family of Renyi divergence to describe the privacy properties of an algorithm, then for both these two approaches, we're using an entire function to describe the privacy property of this algorithm. And Renyi DP use a function of alpha epsilon Renyi DP when epsilon is a function of the order alpha. And when we say a mechanism satisfies rho CDP, is basically says that the Renyi divergence is upper bounded by a linear function with a slope being this parameter rho. Right. So what we know is that the Gaussian mechanism naturally satisfies this property. It satisfies rho the CDP with rho being the L2 sensitivity square over 2 times the sigma square, and sigma square is the amount of noise, the variance of the noise that you add to every coordinate of this query. And one more thing, one more building blocks that we're going to be using today from this RDP and CDP lecture from a while ago is that they both of them imply epsilon delta DP, right? So this will ensure that we have a consistent comparison with the output perturbation and objective perturbation algorithm under epsilon delta DP. So we can see that by simply the turnoff argument and the tail bound lemma for differential privacy, one can show that epsilon alpha RDP implies this differential privacy for any delta. And notice that this holds for all alpha, and we can optimize over alpha by finding the minimum epsilon for every given delta, right? So the alpha that attains the minimum might not be the same for each for each chosen delta. And like one nice thing about CDP and these CDP also have a cleaner conversion into epsilon delta DP. So basically, like it also satisfies an entire family of delta. Since this upper bound of the Renyi divergence is a linear function, so this is effectively just an invocation of the first lemma, and then we can for the any mechanism satisfy rho CDP, we can show that it also satisfies epsilon delta DP for any delta, and the epsilon is given by this quantity, right? So one particular corollary that I wanted to talk about here is that whenever this rho parameter is smaller than log 1 over delta, right? Then this rho is smaller than square root of rho log 1 over delta. And then you can combine these two terms and end up getting just 3 times rho log 1 over delta. Right, so this gives a simplification of the bound, and then say that any rho CDP satisfying this, then we can write its DP guarantees to be so basically rho is equal to epsilon square over log 1 over delta. Yeah, this is equal to epsilon. So this is, I guess, rho is equal to epsilon square over 9 log 1 over delta. Right. So this formula helps us to convert back and forth between epsilon parameter and rho parameter. And for the interesting regimes of epsilon and rho, like you should understand this rho parameter as epsilon square. Okay, so the last thing about the Renyi differential privacy and concentrated differential privacy is that they compose very naturally when you have multiple mechanisms that that's used to access the same data set, and for an adaptive sequence of, say, Gaussian mechanism satisfying like each satisfying rho CDP, then M1 rho 1 CDP and M2 rho 2 CDP, and then the composition of M1 and M2 then satisfies rho 1 plus rho 2 CDP, right? So this makes it very easy for us to just calculate the composition of these mechanisms, and so towards the end of the day, like we can use this to analyze noisy gradient descent and noisy stochastic gradient descent algorithm. Okay, what is this noisy gradient descent algorithm? It's extremely simple. So first of all, the goal, again, is to try to minimize some loss function, the sum of these individual loss function, and sometimes with an additional regularization term, like sometimes not. The noisy gradient descent algorithm. So let's also like give this a name. Let's now today let's call this function, say, f of theta or f of x. Yeah, when we use x to be the parameter of the problem. So the algorithm is simply updating this theta parameter by moving it a little bit towards the negative gradient direction. So the gradient of f of at theta t. But then we differentially privately release this gradient parameter using Gaussian mechanism. And this sigma parameter is chosen appropriately such that the whole thing, like when we run this for t1, 2, all the way to t. Suppose we run this by t iterations, then we'll end up getting like simply a composition of t Gaussian mechanisms. Okay, and the privacy analysis of this, as we mentioned last time, is straightforward. And suppose we want the entire algorithm for t iteration to satisfy rho, then this rho is just equal to t times the square of the L2 sensitivity over 2 times the sigma square parameter. And it remains to just calculate what this L2 sensitivity is, right? So this is a gradient, and this is our query. This is a function that maps the data to R to the D. And we also know that this is equal to the sum over the individual gradient. And in addition, what we're assuming is that each one of these Li is L Lipschitz. Yeah, which says that the gradient of Li is bounded by this parameter L, right? Because this is bounded and this is a summation query, then which implies that the global sensitivity of this gradient has an L2 sensitivity of L. Therefore, this is T L square over 2 sigma square, right? So like two equations that we'll be using frequently in today's lecture is that, first of all, by this equation, and if we calibrate the noise such that the entire t iterations of the noisy gradient descent algorithm satisfy rho CDP, then this parameter sigma square over t, the ratio between the variance of the noise over the number of iterations, is equal to L square over 2 rho, right? So this is the first identity that we'll be using throughout the lecture today. And the second is that the number of iterations that we need to run this. The number of iterations, so this is, we're calculating this for the computational purposes to understand the computational complexity of this algorithm. So the number of iterations that we need to run this is equal to rho times 2 sigma square over L square. Okay, so sigma and t, they are like something at our disposal. We need to choose this appropriately to calibrate the noise to privacy, but we also want to choose them to somehow minimize the error to ensure that given the same privacy budget rho CDP, then we wanted to maximize the performance of the algorithm to get as close as possible to the optimal solution that we're hoping to get for the non-private world. Okay, so a couple of assumptions. Let me reiterate on the assumptions. We're assuming that this Li is L Lipschitz. Sometimes we also assume that this Li is beta smooth. Okay, so when Li is beta smooth and L Lipschitz, then the somewhat conservative upper bound about this function f is that f is n times L Lipschitz, and also like n times beta smooth. Okay, so Lipschitzness is the magnitude of change rate on these functions themselves, and the smoothness is a Lipschitz constant of the gradient. Right, so it's like the upper bound of the second derivative. When this is a multivariate function, this is the upper bound of the largest eigenvalue of your Hessian matrix. Right, so that's what this is beta is, and in the worst case, like this NL and then beta for some data sets, these are like the same, and these upper bounds needs to hold for all theta in the parameter space. Okay, so these are some of our assumptions. We might not need all of that in all our analysis, but these are just to give you an idea on what these notations are about. Yeah, so L denotes Lipschitz and beta denotes smoothness of this individual loss function. And for the summation of the loss function or the objective function that we're optimizing, and they also satisfy Lipschitzness and smoothness property. Yeah, so yeah, we'll also talk about like additional properties when we run into them. For instance, like we want to understand like how well this noisy gradient descent algorithm would perform like in the strongly convex optimization problems. But we'll see that momentarily. All right. So today's lecture is going to be about a utility analysis of the noisy gradient descent. So the good news is that last time we have already done the heavy lifting by analyzing stochastic gradient descent, right? So we came up with some convergence bound of the stochastic gradient descent, and today we're mostly going to be applying the thing that we have already established, so that we can work out the error or the suboptimality of the output of this differentially private algorithm as a function of all the parameters as input, say the privacy requirement, the number of data points, and so on. Yeah, so after that, we'll introduce an extension of the noisy gradient descent algorithm, which is slightly harder to analyze, but we're going to give a sketch of its analysis as well, and to see the relative pros and cons of this algorithm comparing to noisy gradient descent. And meanwhile, like we'll introduce this like highly useful lemma in differentially private analysis called privacy amplification by sampling. And then like once we introduce NoisySGD, and we are all set to talk about the state of the art differentially private deep learning algorithms. All right, so here are some of the readings that we'll be drawing the information of this lecture from. So we will be heavily relying on the theory of the optimization on the convergence of stochastic gradient descent in various settings. And the application, the first application of this convergence result to formally establish these utility bound for the NoisySGD algorithm. So this is not noisy gradient descent, but NoisySGD algorithm was in Basili et al. And they also established information theoretic limit, right? So which implies that a lot of the bounds that we'll be deriving are the best that any algorithm could achieve. So we are really approaching like the limit of algorithm design under differential privacy constraint for learning. And yeah, for deep learning with differential privacy and amplification by sampling and so on. So there are like other references that we'll be drawing information from. Okay, so we'll start with what we have seen from last time. So recall that in the last lecture we've analyzed the convergence of stochastic gradient descent, and in the like almost the most assumption-free setting. So we're not even assuming that these loss functions are convex. So let's say that this f is non-convex, it's possibly non-convex, and how we can measure the convergence rate of this algorithm is by measuring how quickly it converges to the approximate stationary point. Okay, and how we measure something is near a stationary point, we can measure it through the norm of the gradient of these points, right? So on the left-hand side, so this is average square norm of the gradient and taking expectation over all the random variables in the system. So this is expected gradient first order condition convergence rate. And why does this average matter? So using the fact that the minimum is always smaller than the minimum always smaller than the mean. So this is also an upper bound of the mean of all t in t from 1 to t. Expected value of the yeah, I guess the expected value can be outside as well. Gradient of fxt square, right? So this measures the this is also an upper bound of the closest that you get to the stationary point throughout the training. And on the right hand side, so this is a term that depend on the learning rate. So in this case, I'm using constant learning rate. So eta t is equal to eta. And the first and second term, like both depend on the learning rate and depends on all the other parameters of the problems. What I want to highlight is that this n time beta is a smoothness parameter of f, right? So when f satisfy a stronger smoothness property that's not n times beta but something smaller, then you can just replace that parameter over here. And similarly, it goes for the learning rate. Right? When we choose this learning rate to be n beta, and when we to be something that depends on this n beta, then we can replace that with the actual learning rate that this f actual smoothness parameter that this f satisfies. Like in some cases, you can that these are data dependent quantities. In some cases, you can differentially privately release high probability upper and lower bounds of the actual smoothness parameter related to these functions. And we'll see how we can do that like in the last part of this course. Not today. But this goes into the realm of beyond worst case type of data dependent privacy algorithm design. But for now, let's just take this n beta as is and to see what we can get in the worst case when we make no assumptions about the data set. And so from this convergence bound, it remains to choose this eta parameter. So recall that when we derive this convergence bound and construct the telescoping sum, we made the assumption that the learning rate needs to be larger than 1 over the smoothness parameter. So the choice of learning rate is really going to be this the minimum of this quantity and that quantity, right? So the second term is what we get. Suppose we just minimize this over this eta parameter globally, but sometimes we cannot get to do that, and we'll end up getting this this 1 over n beta, right? So you cannot use a larger learning rate than 1 over n beta. Okay, so what's the kind of bound that we'll get? So since this is the minimum of these two, so we'll bound the first term by first and second term by substituting like this learning rate into it. So the first term will be 2 fx1 minus f star over t, and multiply with n. Multiply with a max of n beta and I guess square root of n beta d sigma square t over 2 fx1 minus f star. Okay, and the second term I'm just gonna substitute the second expression in the learning rate bound, because if it is the first that's chosen, then the second is also a valid upper bound, right? So when we substitute that into the expression, then we get then we simply get the square root of n beta d sigma square and 2 fx1 minus f star. F star is the optimal solution over t, right? So notice that the max is smaller than the summation, right? The max is smaller than the summation, so the whole thing is now smaller than just 2 fx1 minus f star over eta over n beta over t, plus I guess 2 times this 2n beta d sigma square fx1 minus f star over t. So let me parse this bound for you, right? So the first term of this bound is coming from the convergence of the gradient descent without noise added to the gradient. Right, suppose there are no noise that got added, and then this bound recovers this rate. So take sigma to be 0, and then you recover the rate of the gradient descent. And the second term, suppose theta is non-zero and is sufficiently large, when the second term would dominate this this expression, then you recover the optimal rate of the stochastic gradient descent. Okay, and so this bound can be obtained by this choice of the learning rate, and now the next thing that we want to do is to figure out like what is our choice of the sigma parameter and t parameter, so that we can write this suboptimality bound or this stationary point convergence bound as a function of this epsilon parameter or rho parameter from the rho CDP. So recall that from rho CDP. Of the whole noisy gradient descent algorithm, we know that rho is equal to t times L square over 2 sigma square, which if we group the sigma square over t together, we know that sigma square over t is equal to L square over 2 rho. So we can simply substitute into the second part of the bound, right? So that gives us some constant times n beta d f x1 minus f fx star So fx1 minus fx star is how far away that you are from your optimal solution from the initialization. So this also makes sense because the closer that you are at your initialization, the smaller number of iterations it takes for you to get to the optimal solution. Therefore, like it's quite natural for the bound to depend on this. And then now let's substitute this sigma square over t, and which just gives us L square over 2 rho. Right? Recall that from what we've seen from rho CDP and this conversion to epsilon delta dp. So in the interesting regime, this is proportional to just n beta d, some suboptimality fx1 minus f star, and over also L square. And rho, recall that it is epsilon square over log 1 over delta. Okay, so that converts it to epsilon delta dp. So how about the first term? How about this term? Yeah, this term is really kind of interesting because if we substitute this choice of t inside here, and we can see, let's substitute t here. We got n beta 2 times fx1 minus f star over our choice of t is 2 sigma square rho, 2 sigma square rho over L square. So L square becomes a numerator. So what is interesting about this bound is that in order to calibrate the noise to this rho CDP, we know that it suffices to calibrate sigma square over t, right? So sigma square and t, they can both go to infinity. But when this rho is a constant, when sigma square and t go to infinity, like this term vanishes as the sigma square go to infinity. So we can make the first term arbitrarily small by using a large noise that got added to this and then use more number of iterations. So if we just dump computation to this problem, at some point, like this term is going to be smaller than the second term. So at the end of the day, the convergence bound, or the utility guarantee will only depend on this parameter. Right? So we can always choose the sigma square and t to go to infinity at the same rate, such that their ratio remains a constant. Right? So it's somewhat counterintuitive, but at the limit, like we are using a smaller learning rate, but we are using a larger noise, and this annealing will ensure that the 1 over t term in this convergence bound is going to 0 faster than the 1 over square root of t term that's going to 0. Okay, so basically what I'm saying is that this term is a right term for our analysis that shows the utility guarantee of noisy gradient descent under this non-convex smooth setting. Okay, so we'll now move to like the case when we add additional assumptions. Let's in addition assume that these loss functions are also convex. Okay, we're also making the same smoothness assumption. So convex and smooth problems, convex, smooth, and Lipschitz problems. Say logistic regression, it satisfies this property. And when we make assumptions about convexity, then we can actually obtain convergence bound about the objective function value. So in this case, the average of the iterations is going to converge to the optimal solution. So f star is equal to the minimum of f. Yeah, so I think I'm using x. It is equal to the minimum the optimal solution of f of x. And what makes this meaningful and interesting is that this is a convex combination of t different points, right? So what this is saying is that we can actually make use of this and construct an estimator so what this is saying is that the expected suboptimality of this particular choice 1 over t sum over t from 1 to t xt minus f star is smaller than the same quantity. right? And this is by the definition of convex function. So recall the definition of convex function that any convex interpolation of the points is going to be smaller than the convex the interpolation of the function values. Therefore, this is always smaller than what we got here. Okay, and the right hand side is also interesting. It looks very similar to the terms that we got previously, except that instead of the difference, instead of the numerator depending on the difference of the suboptimality at the initialization, now the numerator depends on how far away that you are from the optimal solution, how far away that you are from the optimal solution at the initialization. Right, so we can always take this x1 to be just 0, right? So in this sense, it's like, yeah, I don't know if you guys still remember, like from the table of objective perturbation and the output perturbation, like the bounds that we end up getting always depend on this theta star 2 norm, and this is where it could potentially be coming from, like in this context as well. And the last term is the only thing that we need to do again over here is to choose the learning rate appropriately, and the learning rate that we choose is a minimum of the gradient descent learning rate. So this is gradient descent learning rate and the SGD learning rate. Okay, so when the sigma is very small, then it behaves like gradient descent. And when sigma is large, then it behaves like stochastic gradient descent. And when we choose this learning rate as a minimum and using exactly the same argument as before, we can show that this is smaller than n beta x1 minus x star square over t. Plus I guess 2 times x1 minus x star square root of d sigma square over square root of t. Okay, just use exactly the same argument as before, but substitute in this learning rate, like splitting the first term into the sum of 2 things, and then use the fact that the second choice of learning rate is an upper bound of that summation, and multiply this by a factor of 2, then you get the GD's rate and the SGD rate. Okay, so now let's repeat the same argument from the concentrated DP analysis, and to parameterize this bound and substituting this sigma parameter. So what is the sigma parameter that we need to choose? So again, from the target rho CDP of the whole t iterations of running this algorithm. So this is equal to t L square over 2 sigma square. That's coming from the composition of T Gaussian mechanism, and each one of them satisfy L square over 2 sigma square CDP. And with this chosen, and sigma square over T is equal to L square over 2 rho. So I'm just writing the same thing from the previous slide. And then we can substitute into the second term. And that gives us 2 times x1 minus x star square root of d L square over rho, right? So it's a lot simpler than what we have from previously. And again, using the conversion, this is proportional to square root of d L square log 1 over delta over epsilon, right? So something that we expect. So how about the first term, right? So again, the first term like can be made smaller, arbitrarily smaller if we just make sigma bigger, right? Make sigma bigger and t bigger at the same time, so that the sigma square over t like remain as a constant. So how large does t needs to be? So let's large t needs to be for the first term to be negligible. So it needs to be like the first expression of the bound needs to be smaller than the second. To say it differently, n beta x1 minus x star square over t needs to be smaller than x1 minus x star square, and dl square log 1 over delta over epsilon, right? And I guess these two can be grouped together into square root of rho, right? So what this is saying is that t needs to be larger than t needs to be larger than I guess n beta over square root of dl square root of rho, and I guess the nice thing about this is that the like this term got canceled out. Wait, yeah, I don't think they get canceled. I don't have a square here, so it's not exactly canceled out, but then you get this x1 minus x star on top. Okay, so t need to have at least this many iterations, and if we simplify it even further, and then use the fact that rho is proportional to epsilon square, this is something on the order of n times epsilon, right? So we need this many iterations in order for the algorithm to give us the right utility bound as specified here. Okay, so how about we like weaken the assumption slightly? So recall that previously the optimal perturbation is able to work on the setting when the loss functions are just Lipschitz, but not necessarily differentiable. And we know that the gradient descent algorithm and the stochastic gradient descent algorithm has a version of it that deals with subgradient. So when we do stochastic subgradient descent, and this is the convergence bound that we can obtain. Okay, so I'm not showing you how this works, but the key idea of all these algorithms is to carefully choose the learning rate and construct a telescoping structure, and then bound the right hand side by something that divide everything by t. Okay, so the left hand side is the same as before, so it is the expected suboptimality. And the right hand side has a 1 over t term here times the learning rate, and the learning rate times some Lipschitz term and the noise term. So these are coming from the variance of the gradient or subgradient estimate. These are coming from the noise that we add due to differential privacy, and these are the magnitude of the sequence of subgradients that we encountered when we run this algorithm. We can because of we have no smoothness, we have no longer we no longer have this restriction that we need to choose this learning rate to be smaller than 1 over beta, right? So because we don't have that anyhow, and for that we've loosened we lost the monotonicity of the convergence, but that's fine. We can still just work with this by choosing this learning rate arbitrarily to minimize these two bounds. So what we can do is to choose this eta optimally, and that gives us just a product of these two, and yeah, that gives us the square root of the product of these two. And we've worked this out like many times already. So let's just write it out. So we will have this over square root of t, and then the square root of d sigma square plus whatever this term is, right? So for now, let's simplify this by bounding this by the Lipschitz property of f. So recall that f is the summation of individual loss functions, and each one of them is L Lipschitz. So f is n L Lipschitz, Therefore, this is bounded by n square L. This is bounded by n square L square, right? So we can write n square L square here. And we can simplify these terms further into x1 minus x star. I guess just using the fact that x square plus y square root is smaller than x plus y, right? When x and y are both non-negative, like you always have this inequality. And by applying this, we can simplify this bound a little bit further into NL over square root of t plus square root of d sigma square over t. Right? Am I missing anything? Yeah, I guess I missed this x1 minus x star term in the second, right? So this gives us something that's very similar to the previous page, because the second term is what we want because it depends on sigma square over t, and by substituting our expression for rho in choosing the ratio between sigma square over t, then this is and this is x1 minus x star and square root of d L square over rho, right? And this is in terms of epsilon delta dp. This is d log 1 over delta L square in the square root over epsilon square, right? So everything as expected, because L over epsilon is the L2 sensitivity over epsilon, and multiply with this square root of log 1 over delta. So for the first term, for this term, it is the same game again, right? Because now we just need to make this t sufficiently large such that this term is small relative to the second term, so that we can combine them. And in practice, like by dumping computation to it, by increasing this t arbitrarily, like we can make sure that the first term is going to 0. The first term is negligible. Right, we can always do that because the second term only depends on the ratio of sigma square over t. Right, so the bound is optimized at the limit when both sigma square and t go to infinity. So this term becomes negligible. But what we can do is to still calculate what is a marginally sufficient number of iterations for us to obtain this the right rate up to a constant factor of 2. Right. So in order to do that, in order to do that, we need to set this NL over square root of t to be smaller than square root of d L square over rho. Right. In order for this to happen, now these two terms got cancel out, and t needs to be larger than NL square root of rho over square root of d L square, and L also got canceled out, and this is proportional to n epsilon as well. Okay, so in order wait, it's not n epsilon, this is square root of t, right? So this is proportional to so t needs to be larger than n square epsilon square in order for this algorithm, under the weaker assumption to converge to something that's good, to converge to something that's nearly information theoretically optimal. Okay, so the last setting about noisy gradient descent that I want to mention is that it also adapts to the strong convexity of the loss function. Let's say that this f is lambda strongly convex. Yeah, I don't mean that this f is something, the sum of the loss function plus an additional regularization term, right? We can certainly create such strongly convex function, but in some cases, the loss functions themselves are already strongly convex due to properties of the due to properties of the data set. Right, so this lambda, you should view it as a combination of this additional regularization term that you add and the part of the strong convexity parameter that's coming from the data set. And then for that reason, this lambda can be as large as n, can be as large as order n, and when it is small, it is like something like order 1. And if it is order 1, then the effect of this lambda will be somewhat negligible. Okay, so the gist is that, like, when we make an even more assumption, so notice that we don't need the smoothness assumption, we only need the strong convexity and Lipschitz assumptions. When we make these assumptions, then the noisy gradient descent converges even faster to the optimal solution. So from this paper, they provide like 2 very clean analysis for these 2 choices of the learning rate, and the first will give us this 1/t convergence. 1/t convergence. When you choose this learning rate to be that instead of a constant learning rate, now this learning rate is going to 0 at this particular rate. So when we choose these, then we can get just 1 over lambda t. But then there's a logarithmic dependence on the numerator as well. On the other hand, like when we just adjust this learning rate slightly, and then correspondingly we adjust the averaging scheme of these sequence of parameters also slightly. So notice that now each parameter is weighted by t, and this is just a sum of all the weights. So 1 plus 2 plus all the way to t is equal to t plus 1 over 2. Right, so this is how we get this expression, and this is just a weighted convex combination of the sequence of xt. And what under the strongly convex and Lipschitz setting, and then we can knock off this additional factor of log t as well, like using the second learning rate schedule, and that gives us like this bound, right? So we're going to be using this bound in the next slide. To work out the same calculation to see what's the dependence on epsilon and delta, or on the rho parameter of the concentrated differential privacy. So again, like this breaks down into 2 terms. This breakdowns into 2 terms: 4n square L square over just lambda t. So I'm ignoring this plus 1. Yeah, let me also ignore this 4 from some numerical constant in front, and then the second term will be d sigma square lambda t, right? So sigma square, so the sigma square over t, so we've seen this many times already. So this is equal to dl square lambda rho, and rho is our CDP parameter that we require, and the first term. The first term, if the first term needs to be smaller than if the first term needs to be smaller than dl square over lambda p, then we can get the marginally meaningful number of iterations for this algorithm to converge to this parameter, right? Again, this is dl square log 1 over delta over lambda times epsilon square, right? So it's we get some improvement. So notice that lambda is proportional, sometimes proportional to n. So this is really like the 1 over n epsilon square type of rate, right? That goes to 0 even faster than this 1 over epsilon. And we're not even like dividing both sides by n yet, because the f is a sum of the loss function rather than the average of the loss function. So if we divide both sides by n, and this will become like 1 over n square epsilon square, right? So it goes to 0 really fast for reasonable choices of epsilon, right? So now, like, what is the computational complexity to actually get this result that's good on the second term, right? We can always make t infinitely large so that the first term like vanishes. but we just want to do just enough so that we get a good trade-off between computation and privacy. So the choice of t, by just working out the equation, inequality t needs to be larger than n square times rho over lambda, right? And this is roughly like order of n square epsilon square over lambda, right? So when lambda, the largest possible lambda is n, right? So you will just at least the computational complexity needs to be like running the number of iterations being the same as the size of the data set, right? Okay, as a checkpoint, so we've gone over like several different regimes of the noisy gradient descent analysis by combining the convergence rate of noisy gradient descent from the optimization theory, all right, which I gave you a flavor of how it is derived in the last lecture, but today we're introducing a lot more and citing some results that's from known papers. And then we can work out the utility analysis of the differentially private mechanism called noisy gradient descent. And now in this table, let's compare that with objective perturbation and output perturbation. So the first thing to realize is that under these under all these assumptions, under the convex optimization setting, so when the loss functions are convex, noisy gradient descent achieves like exactly the same rate, right? So this is when we choose the initialization, choose x1 to be 0, right? And then x star is a theta star, right? So it's just a slight change of notation. And the only difference in this bound is that now we are dividing, now we are measuring in terms of the axis empirical risk. And this is how much larger you are comparing to the empirical risk, and empirical risk is an average rather than a summation. So that's why this 1 over n factors got applied to all of these bounds, right? So you can see that instead of having like 1 over epsilon, now you got 1 over epsilon times n, right? Which is just a scaling issue, so that all the bounds are comparable to each other. We can see that all these results are the same as that of the generalized linear model that's coming from objective perturbation. Right, so objective perturbation requires additional assumption, like for this tight bound to hold, but noisy gradient descent, when we choose the parameters appropriately, like it will give us the like, this is also the information theoretically optimal. It gives us information theoretically optimal result across the board. And in addition to this, noisy gradient descent are also able to address problems that are not readily addressable by say objective perturbation. So in our analysis, we didn't talk about the constraint case. And for noisy gradient descent, all of these, suppose we just replace this with noisy projected gradient descent, and everything that we've covered so far would apply to that setting as well, without any change at all. So these are the rates that you get from the noisy projected gradient descent. And noisy gradient descent can also adapt to strongly convex loss functions, and when things are lambda strongly convex, and this is the rate that you can get. Like we didn't talk about this, but objective perturbation can also get this for the generalized linear model, but for the Lipschitz and smooth cases, without the generalized linear model assumption, then some additional dependence on the dimensionality is required for objective perturbation. But noisy gradient descent is just a matter of changing the learning rate slightly from when we run it on the general convex problem and the convex smooth problems. And furthermore, so objective perturbation and output perturbation rely very heavily on the fact that these are convex optimization problems because they make explicit use of the optimality condition and the fact that you are converging to a point that is optimal and it satisfies the condition that gradient equal to 0 or the KKT condition when the like sub-differential the sub gradient like contains 0. So in this case, like we can also apply the same kind of analysis to analyze noisy gradient descent for the non-convex optimization setting, and these are the bound that we get, right? It's not like a crazily strong bound because you have this n factor on top, you have this n factor in a bottom, and even after we divide both sides by n, and this and arguably this f. The difference between this f theta 1 to f star could also be something that depends on n, right? So this is the difference in the summation of the loss function. So the scale of this f is order of n, right? So if we put everything together, you have this n square root of n beta times something that's also on the order of square root of n, which cancels with n. So this convergence bound might be trivial in some cases, but in other cases, when we actually have access to a good initialization, such that this f theta 1 minus f star is doesn't depend on n, or suppose we can show that or test that the Lipschitz constant for the smoothness parameter for the summation of all loss function is substantially smaller than n beta, then this also would give us something that goes to 0 as n goes to infinity. Right. So all these are obtained, all these generalizations are obtained without like doing anything beyond just choosing the learning rate differently. Yeah, so to say it differently, NoisySGD is better because it is more generally applicable, and we get like stronger like guarantees, and in addition, like technically speaking, the objective perturbation and the output perturbation requires us to obtain the exact optimal solution to a convex optimization problem, which in practice, we need to resort to numerical computation. And yeah, then the best that any numerical computation for solving this convex programs can give us, say, something that's a epsilon optimal solution, right? When epsilon is, say, the numerical accuracy. On the other hand, noisy gradient descent is incremental. It basically says that all our results apply simultaneously, not just to the final solution that we get, but even to suppose we privately release the entire trajectory of theta 1, theta 2, theta 3, all the way to theta t, right? So the noisy gradient descent output theta 1 to theta t in an entire sequence, whereas whereas like the objective perturbation and output perturbation, they can only output theta hat p, which is either an optimal solution to some perturbed objective or something that got added to theta star plus noise, right? When the theta star, when numerically, when this technically speaking, when this theta star is an approximate solution, then we need to modify our argument in analyzing the global sensitivity of theta star, rather than just using the theoretical bound of the theta star by assuming that it is actually optimal, right? So that's another advantage of NoisySGD, because it doesn't really require the optimal solution because we can stop anywhere, right? In addition, some of these points might be better than the last point, theta t. And then once we release this sequence, we can say, take this and then run report noisy max, right? We can take each one of these and then evaluate it on a sometimes private test data, and then we can output the one that gives us arc max, right? So that's some kind of post-processing that's not doable for noisy for other algorithms. Okay, so we'll take a break for 5 minutes and we'll resume at 2:12, and then we'll talk about some subtle issues of noisy gradient descent in terms of computation, and then like move on to noisy stochastic gradient descent, and the differential privacy departing. All right, see you in a little bit. All right, everybody, it's 2:12. Let's resume the lecture. So far, we've been talking about the utility analysis of the noisy gradient descent mechanism. We've seen that it is a lot more flexible and often obtains stronger utility bound comparing to objective perturbation. Right, so there's one shortcoming of this algorithm comparing to the objective perturbation is that it requires us to set learning rate, optimally set learning rate, and sometimes that optimal choice of the learning rate would depend on unknown quantities. Like if it does, then you get something that's slightly weaker. But other than that, like converting a problem into tuning of tuning many different parameters to just tuning one parameter, the learning rate is an interesting progress, and it concretely and if we ignore computation, a noisy gradient descent is able to like solve a much broader family of problems with optimal dependence on everything. Okay, so let's talk a little bit more about the computational complexity of noisy gradient descent, and then we'll see like whether this kind of computational barrier can be resolved by running like a different version of noisy gradient descent, but called noisy stochastic gradient descent. Right. So far we've been seeing a consistent pattern among all these convergence bounds is that there are two terms, and the first term goes to 0 if t goes to infinity, and sigma square goes to infinity, and sigma square and t, their ratio will remain a constant, which is set to the CDP parameter rho, set to be proportional to the CDP parameter rho that we set ahead of time. So the first term can always vanish, but we wanted to calculate like how large this t needs to be for the impact from the first term to become negligible, right? So we've worked that out for various settings, but now let's write it down concretely. So for convex and Lipschitz case, for the like weakest assumptions, the convex and Lipschitz case. I guess we need this t to be larger than n square rho x1 minus x star d, right? We need this t to be larger than this quantity, and this is proportional to n square epsilon square. Right. On the other hand, notice that like this could benefit from a larger dimensionality. So when d is large, then the number of iterations you need to run this is small. But at the end of the day, like it still requires you to run like n square epsilon square number of iterations. And notice that in every iteration you need to go over the entire data set, right, to calculate the gradient, right? So that could make this like not so great, because every iteration you need to go over every single data point. So in terms of the number of incremental gradient oracles, so incremental gradient oracle. So this is how the optimization people oracle yeah. So this is the evaluation of the gradient of like one of this individual data point. So each call of these would call like one call of this incremental gradient oracle. And since every iteration requires going over the entire data set and then compute the gradient, and then the total number of calls to this this gradient oracle is n cube epsilon square. Yeah, for convex and smooth problems, the situation is a bit better. So we've seen that this t is larger than n beta square root of rho x1 minus x over square root of dl. Right. So this is This is roughly roughly n times epsilon rather than n times epsilon squared. So it's a lot better. And when we have smoothness, then the computational complexity the compute, what's going on? Sorry about it. The Apple Pencil suddenly starts to behave strangely. So let me try fixing this to see. Okay, now it works. So the number of calls, incremental oracle calls is order of n square epsilon. All right. And in addition, when we have the strongly convex problem, in order to adapt to the strong convexity, we've seen that T needs to be larger than n square rho over D, right? And this is on the order of, again, n square epsilon square, right? So the part of the reason that why we need this is because we're not making smoothness assumptions. So for those problems that are simultaneously smooth and strongly convex, then we can potentially improve this into something on the order of n epsilon. But so no smoothness, only strong convexity, and in this case, like this is a kind of a number of iterations, and the number of incremental or gradient oracle calls is n cube epsilon square. So all these are crazily expensive operations because going over the data set for n squared times like makes this algorithm like not so practical. So for this reason, like there has been a line of research on trying to retain the information theoretic limit, the same kind of privacy utility trade-off, but achieve that with a much smaller number of iterations. Say, is there a one-pass algorithm that allows us to get the same result? Yeah, and that line of research is still ongoing. Like what we know is that getting sub-quadratic dependence, getting something that's better than this is actually like highly non-trivial, provably. On the other hand, like for generalized linear models, the objective perturbation algorithm, like it is something great because we're just perturbing the objective function, and then we can use any numerical tools to optimize it. So just now I'm talking about the limitation of that, because any numerical tools can only give you a solution with finite accuracy, which in some sense breaks the theoretical analysis, which holds in the idealistic situation. But on the other hand, to decouple the privacy and the optimization has the additional benefit that it doesn't require us to update for this many iterations, right? So we can just use non-private optimizers without adding noise, and that gives us the same privacy utility trade-off, but much faster in terms of its computation. Okay, so one natural idea is to say, instead of using the noisy gradient descent, can we use noisy stochastic gradient descent? Because stochastic gradient descent is the kind of algorithm that people use all the time, like in the context of just scalable optimization, because it really allows us to just go over the data set sometimes for once, or sometimes for 10, 20 times, and we're already like very near the optimal solution, right? We don't really need to go over the data set for that many iterations. And the answer is yes. So there's a version of the noisy gradient descent algorithm called noisy stochastic gradient descent algorithm that adds noise to the randomly chosen gradient computed on the mini batch. And the key underlying idea there is that we are not only relying on the noise added to the gradient to the mini batch gradient calculated on the mini batch to obtain the privacy guarantee, but instead we are relying on this random sampling of the mini batch as well, right? So let's say that this mini batch is sampled randomly from the given data set, And also, like then once we calculate the stochastic gradient on this mini batch, we'll add noise to it. So this one, this algorithm is the noise adding. It can be Laplace noise or Gaussian noise. So for this class, we'll be just using Gaussian noise. But the privacy mechanism is not about just analyzing this Gaussian mechanism, because that will not take into consideration of the random sampling, which turns out to be very important for the tight analysis of the differentially private stochastic gradient descent. Okay, so this lemma says something very interesting. So it's called subsampling lemma, also known as also known as the secrecy of the sample. So the idea is the following: suppose you are part of a data set of n copies of individuals, and if the like differentially private processing is conducted on a random subset of the data, then there is a chance that you are not actually in the data set that's being processed, right? So there's only a fraction of the probability that your data will be processed. Let's say that you are the person that got added or removed from the data set, and if there is a chance that this data point is not included in this sample, then in those cases, the two neighboring data set is going to give us exactly the same distribution, right? Only when this additional sample happens to be part of this mini batch that we choose, will there be like privacy loss that's incurred? Will the conditional like privacy loss random variable be something that's not a singleton that's supported at 0 like throughout? Okay, so that can be formalized by this lemma, which I skipped the proof, which says that if you have an algorithm M, that before you apply this DP algorithm M, you first sample your data set. You sample your data set with some sampling ratio gamma parameter, and then at the end of the day, you are getting epsilon prime delta prime DP with delta being gamma times this like original delta, and epsilon prime being converted into through this nonlinear transformation of this log 1 plus something, and when this epsilon is small, like you can see that this log 1 plus something is just roughly the same as that is roughly the same as a second term, and you will end up just getting gamma times, say, 2 times epsilon. Right, so that's called privacy amplification by sampling, or subsampling lemma, or also known as the secrecy of the sample. It talks about how your privacy guarantee can get stronger with a pre-processing step by randomly choose just a subset of the data. Okay, and this is nice because that's exactly how stochastic gradient descent works, right? So in stochastic gradient descent, we choose a random subset of the mini batch, and then I calculate the gradient there. With appropriate scaling, I can make it the unbiased estimator of the original gradient. So there are some subtleties here on how people practically implement this algorithm. And specifically, there are 2 types of different sampling schemes that both give you the same privacy amplification by sampling result that stated exactly the same. So they are the Poisson sampling and sampling without replacement. So Poisson sampling works as follows. Poisson sampling with a parameter gamma. So include data point I in the mini batch by tossing an independent random coin by sampling from a Bernoulli distribution with probability gamma. So by tossing a coin with probability gamma or with probability gamma, and not include let's not include this data point with probability 1 minus gamma, and everything is independent. So notice that when we do this, the size of the mini batch is actually a random variable, right? So the expected size of the mini batch is the expected value, expected size of the mini batch is equal to gamma times n. But in reality, we can get anything like between 0 and n, right? So this notion of sampling and works really well with the add or remove version of the differential privacy, because the add or remove version of the neighboring relationship would require your mechanism to be applicable to all data sets with arbitrary lengths of the data set, right? So no matter what this batch ends up being, and then your algorithms that got applied to this batch satisfy epsilon delta dp, or satisfying the RAIN EDP, like will have a meaningful notion of privacy there. And another thing that is nice about this is that in order to implement this algorithm, you do not actually need to know this parameter n, right? Which n is a sensitive information, and is the size of the data set is also part of the information that we need to protect. So this works well with add or remove. Like another type of more commonly used sampling scheme that's typically used in machine learning is called the sampling without replacement, or random subset sampling. So this basically choose any subset of size m from 1 to n. Choose any set with the size of the batch being m from the data set, right? So this ensures that the size of the batch is always equal to m, and then we basically define this gamma to be m over n. So this is really like finding a random subset, and each subset has a uniform has an equal probability to be chosen, and this notion of amplification by sampling works really well with a replace one like neighboring relationship. So if you add or remove individual, then the two neighboring data set actually has the same cardinality. So in this case, both m and n, they are public information, because no matter what the data sets are, adding or removing individual doesn't actually change that. And then we can talk about mechanisms that applies only to data sets of a particular like given size, with the size of the data set being public information. Okay, and in practice, Poisson sampling is what people typically analyze, but when people implement the algorithm, sometimes they're not taking they're not being very careful in implementing their differentially private algorithm, and then use the random subset selection, which has the implication of now the definition of DP is slightly different, and the sensitivity is sometimes a factor of 2 larger, and yeah, taking care of all these would lead to sometimes a little bit of drop in the performance that you would have gotten like with Poisson sampling. Okay. So I've shown you the amplification by sampling lemma for epsilon delta dp. So there's also an amplification lemma for the RAIN differential privacy. So the idea is that if m satisfy like epsilon alpha dp, then suppose we sample the data set and then apply m, so satisfy some epsilon prime alpha differential privacy, and then the amplification privacy amplification result is a transformation from this epsilon function to this epsilon prime function. Okay, so what I'm plotting here shows the RAIN EDP conversion formula that gives you that goes from Gaussian to sampled Gaussian. So on top, this green line is the RAIN EDP of m of a Gaussian mechanism. So say if we choose this gamma to be 0.01, then you can see that like the transformation is actually somewhat complex, right? So both of these are showing in the logarithmic scale. So this is log of alpha, and the vertical axis is a log of the Renyi differential privacy. Renyi differential privacy upper bound. So we see that in those regimes when the alpha is small and this phase transition happens roughly at this phase transition happens roughly at epsilon e to the power of epsilon alpha minus 1. Yeah, I think there's another alpha roughly this over gamma. Right, so when alpha is larger than this, then basically you do not get any benefits from amplification by sampling. But when alpha is small, then the Renyi differential privacy actually satisfy like about the same amplification factor, where you can see that these are more or less gamma square like epsilon alpha, and this is our epsilon alpha. Okay, so again, like there isn't a privacy amplification result for concentrated DP for exactly this reason, because the best possible linear upper bound for these orange and blue curve is actually just this green line, right? So you're not getting anything better from the concentrated DP, but using the full Renyi DP analysis will allow you to represent a more complex function like this, which would allow you to operate within the regime where you actually get an amplification of the RDP parameter by a factor of gamma square, right? So you can actually read that off from the vertical axis. This is around 1. This is 10 to the power of minus 4 minus 5. Okay, so the square of this is gamma parameter. Okay, so for our analysis now, we're just gonna be like operating around this region where this amplification has an effect, right? When it doesn't have an effect, then it doesn't make sense to do noisy stochastic gradient descent. But when we are operating within this region, then we can get some kind of a truncated version of the concentrated differential privacy to simplify the analysis, because both of these are bounded from above by some linear functions up to some region of interest. Okay, so this is called the truncated concentrated differential privacy that was developed previously as an analytical tool. So all of these are only useful for you to analyze algorithm and write down the asymptotic dependence in a clean language. And in practice, you'll be using numerical tools like AutoDP to directly represent these more complex functions and then do numerical optimization over those alphas to obtain the best possible epsilon delta trade-offs. Okay, but for today, let's pretend that that the subsample mechanism actually just satisfy gamma square rho CDP, right? So satisfy gamma rho like truncated CDP, and then work with this linear upper bound for the restricted region. All right, so now we're ready to state how this noisy stochastic gradient descent algorithm works. So the NoisySGD algorithm update the parameter by moving towards the negative stochastic gradient direction. So some GT. And what is this GT? Yeah, this is for t from 1 to t, and we also need to add noise to this approximation. Yeah, but yeah, let's include this noise in this GT definition itself. So what is this GT? And GT hat is equal to first of all, the sum over all the data points that got chosen in this random mini batch, and from that mini batch, I can compute the gradient of this corresponding loss function at theta t, and I can use the Gaussian mechanism to release this sum of the gradient because it has sensitivity L2 sensitivity L. Okay, So let's add a bracket here. So that's what we released using Gaussian mechanism, but this is not an unbiased estimator of the original gradient. So recall that the original gradient is the original gradient is a sum over all individuals. So this is a gradient of interest. Okay, so in order to make this an unbiased estimator of the gradient, we have to add a scaling factor of 1 over gamma to offset the fact that only the gamma fraction of the data points are chosen in expectation. Right, so what is random? So in this case, the size of the batch is random. Therefore, like all these indices I is random, and this noise in addition to this is random. Yeah, so basically like this is what we get, right? So you can leave this as an exercise. You can show that this g hat t given theta t is equal to the gradient of theta t. So with this, it's clear that this algorithm with this update rule is a particular instance of the stochastic gradient descent algorithm because it satisfies the condition that g hat t is an unbiased estimator of the gradient, and like it has a bounded variance. The variance now is coming from both the additional noise that we add and the noise that's coming from sampling this mini batch. Okay, the privacy analysis of this is straightforward because this is just a composition of T subsampled Gaussian mechanism. We've seen that the Renyi differential privacy looks like something that grows linearly and then it jumps up and then converges to the other linear function that's coming from that of the Gaussian mechanism without amplification. So simply multiplying that by T, and in that interesting regime, then we can basically get that rho like T truncated CDP, and this rho is roughly gamma square multiply with the 2 sigma square delta square, and delta square is a global sensitivity, which we know that it's the Lipschitz constant L square, and also multiply with a number of iterations. So that's the rho TCDP parameter of the noisy SGD algorithm by running this for T iterations. Okay, and from there, like if we pretend that this holds for all regimes, and for some regimes, like the optimal solution of this alpha by finding the RDP to DP conversion will end up being in this nice region where we have the amplification effect, and like under that regime, the conversion from this rho to this epsilon delta parameter is roughly epsilon square log 1 over delta. Yeah. Conversion in nice regimes. Okay, so in practice, we don't need to do this. Like we basically just call numerical tools, but the like for the sake of theoretical analysis, we want to understand the scaling, and this is the kind of scaling that relates rho to epsilon and delta. So even in a truncated version of the CDP analysis. Okay, so how about the utility, right? So the gradient estimate, as we've seen, is 1 over gamma, and sum of this random batch and the gradient of the individual parameters plus noise. Right, so this is our gradient estimate. It is still the unbiased estimator, and everything, all the theoretical analysis is exactly the same as before, because this is just another instance of stochastic gradient descent. But the noise parameter just got a little bit bigger. So whenever previously we have d sigma square, now we will have something that's a lot bigger. So we will have we will have d sigma square over gamma square. So this is a part of the noise that's coming from this is a part of noise that's coming from our Gaussian mechanism. So this is our added noise, but that's not the only source of the noise. There's also a source of the noise that's coming from the random sampling of the mini batch, right? For this random sampling of the mini batch, so notice that this is a summation of this is a summation of n random variables, and some like this is summation of n random variables, and we can rewrite this to be first of all 1 over gamma, and the indicator of I is chosen, and this I theta t, right? And we know that this is bounded by L. The norm is bounded by L, and this is bounded by 1, right? So we can apply Hofstein's inequality to show that the whole thing is smaller than with high probability. This is smaller than 1 over gamma square root of n. Yeah, but this is not really a good bound, because in a lot of the cases, this indicator is going to be 0, because gamma is small. We're not really choosing anything well. And because gamma is small, we can calculate the variance of this, because this individual random variable. So let's call this random variable xi. Xi is bounded, and it also has a large probability to be exactly 0. So the expected value is actually quite close to 0. So suppose we use the Bernstein's inequality, and then we can get a tighter bound that depends on the variance. And as a matter of fact, for the matter of differentially private analysis, all we need is a variance of this random variable, right? So we don't need a high probability concentration. So we can work out the variance, and I won't give you the details, but I hope I can convince you that this variance is smaller than gamma times L square, right? So the variance is smaller than gamma times L square. So then the summation of n copy of this will give us yeah. So the E of this minus its expected value square. So this is proportional to d sigma square gamma plus n times gamma L square over gamma. And this over gamma is coming from this multiplicative factor. But since we're multiplying this to the variance, we need to square this, and then these two got canceled out. Then what we get, the total variance is d sigma square over gamma square plus n L square over gamma rather than over gamma square. Okay, so that's the kind of bound that we get, and then what we can do is to substitute this bound into one of these like convergence guarantee, and then we'll see then we'll see like what we can end up getting. So which one shall we try? Should we do the strongly convex case, or should we do the convex and smooth case? Let's see. So which one is the easiest? So maybe let's do the convex and smooth case. All right. So if we do the convex and smooth case, then this bound is 2n beta x1 minus x star square over t plus, so this is convex and smooth, square root of d x1 minus x star square sigma square over t, right? So now like we're saying that we're replacing this d sigma square into something else. So let's not worry about the first term. Let's talk about only the second term, and then this becomes d x1 minus x star square, and the sigma now becomes d sigma square over gamma square, and then plus this additional term of n L square over gamma. Okay, so you can see that this is what we're getting, and using the same kind of bounds that we derived previously. This is smaller than this is smaller than. So I'll first keep this, and then I'll write the t d gamma square sigma square plus square root of n L square gamma of t. Okay, so recall that from the CDP analysis, this is like our choice. So in some sense, when we set this rho parameter and assume things remain within the nice regime, then what we know is that the sigma square over t gamma square. So this is something like a constant. So this is equal to L square over 2 rho, right? So now let's substitute this back into the expression by replacing this with replacing this part of the bound. What we get is square root of d over square root of d over L. Wait, where did they go? Okay, d over L square over rho. Right, so this is exactly the same as what we got for the noisy gradient descent case, and the remaining term is something that can actually go to 0 as we increase k, as we increase the number of iterations. So since all we want is this sigma square over t gamma square to be a constant, then this gamma times t can actually, the gamma times t can actually go to 0 if we increase this sigma arbitrarily, right? So when sigma goes to 0 arbitrarily, right? So to say it differently, so in the nice regime at least, then we're getting exactly the same bound as that of the noisy gradient descent. But the difference is that now this residual term, so besides this residual term, there's another residual term that's coming from this term that we have to set t to be somewhat large in order for both these two terms to give us something that's on the same order as the term that we actually cares about. Okay, so that's the idea how we will analyze the noisy stochastic gradient descent. So we've seen that information theoretically in a nice regime with that as a qualifier, then the NoisySGD actually gives us the same result as a noisy gradient descent. So both of these two algorithms is able to achieve the information theoretic limit, no matter how large we choose the mini batch size to be. On the other hand, there are subtle differences in terms of the computation, that one may need like more iterations and more incremental gradient oracle calls in order to achieve the same result, which like deals with increasing sigma and how to use a larger number of iterations to anneal and average away all that noise that we add. Right, so we're out of time today, but we'll finish the calculation and then precisely write down the computational comparison between the NoisySGD and the noisy gradient descent, and then we will talk about the differentially private deep learning, how we apply NoisySGD to this setting, and some other like practical algorithms in the next lecture before we start the data-dependent DP analysis chapter. All right, yeah, thank you everybody for coming. I'll see you guys next Monday.